Okay, and so let's take a look at your activity 18, that is your general properties of proteins. Okay, so let's take a look first at your proteins. Okay, and so accordingly, and so your proteins, and so the arrangement of your amino acids in kind and in number is responsible for a variety of complex proteins. Okay, and so they are the again, and so the arrangement of amino acids and in kind and in number, and so if you have more of amino acids, if you have different kinds of amino acids, then they what you call this, they are responsible for a variety of your complexity of your proteins. Okay, and so your protein substances, they share certain common properties, and so you have here. Okay, and so accordingly your proteins, when they are pure, and so they are generally tasteless, no, and so they are generally tasteless, and so they are also colorless amorphous compounds, and then they have varied degrees of solubility in water, salt solution, dilute acids, and in alkalis, and they form non-diffusible colloidal solutions or colloid solutions of the emulsoid type. And so that emulsoid type is a, what you call this, physiologically has a great importance, no? And so back to tasteless. And so proteins are generally tasteless. No, however, and so your hydrolysates like your proteoses, your peptones, your peptides, and your amino acids accordingly are bitter. No, and so not all, but then not all actually of your amino acids are bitter. And so as we talked in the other video, no, and so your proteoses, your peptones, your peptides, and amino acids, they are bitter. Okay, and so and again, they are your proteins, they are colorless amorphous compounds, and then they have varied degrees of solubility in water, salt solution, and dilute acids and dilute alkalides also, and they form a non-diffusible colloid solutions. Okay, your proteins are amphoteric. Okay, and so your proteins are amphoteric here, and so accordingly, they what they call this, they can behave as either an acid or a base. No, and so that is due to the presence of your uh, carboxyl group and your amino group in the amino acid. Okay, and so accordingly, at a pH of 7, and so your carboxyl group of an amino acid is in its conjugate base form, while the amino group is in its conjugate acid form. Okay, and so with that carboxyl group and that amino group, and so the presence of that gives you your amino acid amphoteric. Okay, and so and then your proteins are labile. Okay, and so your proteins are labile. Okay, and so they are easily modified in solutions when they are subjected to what they call this varying pH, and so ultraviolet rays, heat, and temperature, and so extremes in temperature, and of course organic solvents. No, and so you have there. Okay, and then they are very reactive and highly specific. Okay, and so they are very specific and highly they are very reactive and highly specific. And so due to the presence of side chains and active groups of amino acids still. Okay, and so that is for your proteins. Again, they are amphoteric, labile, and very reactive at high and highly specific. Okay, and so your proteins, they have definite solubility in a solution. And so they have your homogeneous proteins, they have a definite and characteristic solubility in a solution of fixed salt concentration and of pH. Okay, and so of course, under this condition, and so the amount of protein dissolved, and so to form a saturated solution is independent of the excess solute present in the fluid. And so with that, and so giving you that, and so again, the amount of protein dissolved to form a saturated solution is independent of the excess solute present in the fluid. With that, and so what you call this, it provides you your sensitive test for the purity of protein. Okay, and then your proteins differ in their solubility, and so there is a they differ, and so unlike for your homologous ones, no, and so your proteins differ in their solubility, and this solubility is used for the separation and purification of proteins. Okay. Okay, and so let's take a look at the influences to the solubility of proteins. And so first on the list, and so you have your effect of neutral salts. And so your effect of your neutral salts accordingly at a low concentration of neutral salt, and so the solubility of protein is increased. Okay, and so again, at when there is a low concentration of of neutral salts, the solubility of proteins is increased. And so this one is referred to as your salting in effect. Okay, and so this salting in effect is due to the fact that uh, the solubility of proteins at low salt concentration is due to the fact that the solubility of any substance depends on the relative affinity of solute molecules for each other and for the solvent. Okay, and so any factor accordingly that will decrease the interaction of solute molecules will tend to increase the solubility. Again, and so any factor which decreases the interaction of solute molecules will tend to increase the solubility of the solute. Okay, and so the small ions of neutral salts will interact with the ionic groups of protein molecules. And so the small ions of neutral salts will interact with the ionic groups of protein molecules, and so diminishing protein molecule interaction. And so it will diminish protein molecule interaction and it will increase the solubility. Okay, and then that is for your salting in effect. And so that is for your salting in effect. And then you have your salting out. And so at high concentration of solutes, and so it causes the precipitation of proteins. And so at high concentration of salts, and so it causes the precipitation of proteins. And so this is referred to as your salting out effect. Okay, and so it depends on suppression of charges on the surface of the protein and the removal of a shell of water from around the protein molecule by competition of the ions of salt for that water. Okay, and so again, and so a removal of a shell of water around the protein by competition of uh, ions of the salt for the water. And so accordingly, the surface charge and the water of hydration are the two chief factors in keeping the hydrophilic colloids in suspension. Okay, and so it is accordingly easy to see how an agent which suppresses the charge and dehydrates the particle can cause precipitation. Okay, and so that is for your solubility with your neutral salts. Okay, and so let's take a look at the effect of your influence of pH on the solubility of your proteins again. And so your proteins are uh, the solubility of your proteins is influenced by pH, and so that is because of their amphoteric property. Okay, and so but that is they can either be acid or base. And so they can either be acid or base. Okay, and so your solubility is minimum at isoelectric point. And so again, what is your isoelectric point? That is the net charge of that is the pH wherein the net charge of the protein is at 0. No, and so thus, again, so the solubility of your protein will increase with the increasing acidity or alkalinity. Okay, and so with the increasing acidity or alkalinity, and so with this, you already have a charge. And so if you have a what they call this, you have your acidic one, and so if that is below your isoelectric point, they have your proteins have a positive charge, and above your isoelectric point, their pH is at negative, their charge is negative, no, and so With that, and so your isoelectric point, the electrostatic repulsive forces between solute molecules are at a minimum, no? And your crystal lattice forces in the solid state will be maximum, okay? And so when you have your proteins that are amphoteric, exist predominantly as either anions or cations, they are positively or negatively charged. Ayan. And so repulsive forces between ions are high. And so and then of course your since all other molecules possess excess charges at the same sign, and so in this state they will be more soluble than in the isoelectric condition. Okay, and so with that, of course, if you have a, sabi ko nga kanina, if you have a, what you call this, if you already change the pH of the solution, and so then you have an excess of what you call this excess of the charge, no? And so you have again, and so your proteins will have a positive charge at below 7, and so if the solution is acidic, and so then they have a positive charge and a negative charge at a pH of alkaline. Okay, and so giving you the solubility will increase with the increasing acidity and alkalinity. But then, wait, your acids and your bases will precipitate your proteins. And so that is through in denaturation. And so that is true in denaturation. Okay, and so your acids and your bases will precipitate your proteins. But then, accordingly, excess acids will redissolve the precipitate, sorry. And so your excess acid accordingly will redissolve your protein. Okay, and so your inorganic acids and so will precipitate your proteins. Ayan, so, will actually, and so this one, what I'm talking here is in case of your urine. Again, your inorganic acids will precipitate your proteins. And so, and excess acid accordingly will redissolve your precipitate. And so this one is true of your Heller's test, no? And so that is for that. But then for the effect of your pH, you follow the uh, the statement earlier. Okay, and so let's take a look at the influence of organic solvents in your solubility. Okay, and so accordingly, and so when an organic solvent that is miscible with water, and so is added to aqueous solution of protein, and so what are these organic solvents that are miscible with water? And so you have your alcohol, your methanol, your ethanol, and your acetone. And so when this organic solvents is added to the aqueous solution of proteins, and so it will actually lower the dielectric constant. And so it will actually lower the dielectric constant so that the electrical forces between the charged particles in the solution are actually increased. And so they are increased, thus diminishing the solubility of proteins. Okay, and so but then, and so your high concentration of alcohol may dehydrate the protein and will affect the solubility. Okay, and so that is for your effect of your solvents. Okay, let's take a look at your what you call this, precipitation by heavy metals. Okay, and so your precipitation by heavy metals. Accordingly, and so your proteins are precipitated from an alkaline solution by your salts of your heavy metals, no? And so you have there. And so your heavy metals, they precipitate your proteins and your proteins behave like an acid to form insoluble salts with alkaline metals. Okay, and so again, and so they say your proteins behaves like acids by virtue of the presence of your uh, carboxyl radical present in their structure. And so will form your insoluble salts with your alkaline metals. And so usually your mercury, your silver, and lead are actually used with this one. Okay, and so they disrupt, and so your salt bridges by forming ionic bonds with negatively charged groups. Okay. And so your heavy metals again, like such as your mercury, your lead, and your silver, and so will affect your protein structure. How? And so in a way that they will disrupt your salt bridges by forming ionic bonds with your negatively charged groups. So, no, and so your heavy metals will also bond with your sulfhydryl group, and so they will also bond with your sulfhydryl group. And so this one is a process that may result in the changes and in the protein structure and function. Okay, and so again, and so they will also disrupt your salt bridges by forming ionic bonds, and then binds with your SH, your sulfhydryl group, to cause a change in the structure and function of the protein. Okay, and so that is for your precipitation by your heavy metals. And so let's take a look at your action of your heat. And so accordingly, and so, what you call this, when you burn, and so when you burn your proteins, and so they decompose. And so when you burn your proteins, they decompose, and they will, what they give you, will give you a characteristic odor of a burnt hair or feather. No, but then, and so the action of your heat, and so accordingly at 38 to 50 degrees Celsius, there is a slight intramolecular rearrangement. And so there is a changes in the physical, chemical, and biologic properties of the proteins. Okay, and so your protein, and so with this, your protein is insoluble at isoelectric point, and with that, it will form precipitates. Okay, and so it will form precipitates. Okay, and so that is for your action of your heat. Okay, let's take a look at your denaturation. And so again, your denaturation here, this is what you call this, the your intramolecular rearrangement of a protein that causes a change in the physical, chemical, and biological characteristics of a protein. And so high temperature, low temperatures, high pressure, ultraviolet rays, and mechanical shaking, and chemical agents will, what they call this, these are actually agents that will or these are actually circumstances that can denature a protein. Okay, and so a high temperature, you have your heat, the increased heat, and so it has the ability to uh, what they call this, denature your protein. And so your denaturation accordingly is believed to be due to the unfolding of your characteristic folded structure of your polypeptide in your native protein. Okay, and so in your native protein molecules. Okay, and so if you have a denatured protein, and so in the denatured state of your protein, and so the polypeptide chains are randomly and irregularly looped or coiled, no? And so and the conformation of any given polypeptide may change with time. Okay, ayan, so you have there in your in if it is not denatured, and so that you have the characteristic repeating units of folding, no? And so but then in case of this one, you have here irregularly looped or coiled, and the conformation is changed, no? And so that is for your denaturation. And so your denaturation, and so will give actually the protein insoluble at isoelectric point. Okay, and so your denaturation will give your protein insoluble at isoelectric point, and so causing them to precipitate. Okay, and so that is for that. Okay, and so your denaturation again, and so denaturation will make your protein insoluble at isoelectric point. And so let's take a look at your precipitation and coagulation, no? And so your precipitation and coagulation, these are actually forms of denaturation. And so your precipitation and coagulation, they are forms of denaturation. And so your precipitation, that is at what they call this slight extent in a way, and that is irreversible, while your coagulation is uh, irreversible, and that is at a greater extent. No? Ayan, so you have there your denaturation again, ayan, so renders the protein insoluble at isoelectric point. Ayan, so thus, At isoelectric point, it will cause your protein to precipitate. Okay, and so that is a process known as a precipitation. Okay, and so the precipitation of a denatured protein is reversible. And so you have there. And so, okay, and so that is irreversible, no? And so your precipitation is a simple clumping together of your dispersed chains of denatured protein. And so when the forces of your repulsion are mutual repulsion are at minimum. Okay, and so when you heat the precipitated proteins, and so when you further heat the precipitated proteins at higher temperature, and so the precipitated proteins are are actually when you heat, and so your precipitated proteins at higher temperature, or you further heat at higher temperature, or you further what you call this subject them into your denaturing conditions, and so they will what you call this the proteins will form clump chains and they become matted together, and so in a mass which is insoluble. Okay, and so that is in the clumps of proteins are matted together in a mass, giving you a coagulum. And so giving you a coagulum. And this, what they call this mass of proteins is insoluble. And so insoluble not only at isoelectric point, but also over the entire range of your pH. Okay, and so again, this is your coagulation. Okay. And this coagulation process is irreversible. Your precipitation, this one is irreversible. I mean, sorry, your coagulation is irreversible and your precipitation is reversible. And so sorry for that again. And so precipitation is reversible while your coagulation is irreversible. Okay, and so let's take a look at your denatured proteins. And so your denatured proteins are actually more viscous and they are no longer crystallizable. And your denatured proteins are easily digestible by proteolytic enzymes. And then your coagulated proteins, and so your coagulated proteins, they are hard to dissolve. And so they are hard to dissolve. And when they are dissolved, it differs from the original protein. And accordingly, your coagulated proteins, and so the process is irreversible. Okay, and so that is again, and so your denatured protein, and so they are more viscous and they are not crystallizable, and they are easily digested by proteolytic enzymes. Okay, and so that is for your denatured protein. Okay, and so your fractionation of your proteins. And so what is actually the importance of this fractionation? Okay, and so of course, first on the list here, and so your protein fractionation generally refers to the process of isolating, identifying, and characterizing various proteins present in a sample. Okay, and so you have here your methods in fractionation, protein fractionation. You have your precipitation, chromatography, gel filtration, and electrophoresis. No, and so you have there. And so what are actually your what they call this importance of this of fractionation of your proteins. And so with this, of course, you're going to isolation of your plasma proteins. Okay, isolation of plasma proteins to clarify actually the characteristics and components and the function of this protein. And then your protein fractionation, and so this one is used for the diagnosis of diseases also, and this one is used in therapy. And so like yeah, and so the globulin fraction of a protein is used for immunization, passive immunization. The albumin, and so the albumin fraction is used for the treatment of shock, nephrosis, and cirrhosis. And so you have there nephrosis, and so you are excreting more of albumin of protein. In your cirrhosis, you have a diminished capacity of synthesize to synthesize proteins, no? And so that is why you need supply of protein. Okay, and then your fibrin film and fibrin foam, and so accordingly, these ones are used in surgery, and then your agglutinins, and so they are used in determining the blood group of an individual. Okay, and so that is your importance of protein fractionation. Okay, let's take a look at your precipitation again by your heavy metals. Again, your protein behaves like acid. Okay, and so your protein behaves like acid. And so due to the presence of carboxyl radical. And so this carboxyl radical forms insoluble salts with alkaline metals. And so what are those commonly used? You have your mercury, silver, and lead. Okay, and so your heavy metals such as mercury and lead, and so again affect your protein structure in several ways, and so by disruption of the salt bridges and by forming ionic bonds with negatively charged group, and then with your sulfhydryl group as what we stated earlier in this video. Okay, and so again, what are your heavy metals that are used here? Most commonly used, you have your mercury, your silver, and your lead. Okay, and so accordingly, in case of since this one is used in uh your mercury, your silver, and lead, they form insoluble salts with alkaline metals. And so you have your egg white and your milk accordingly are used. Uh, and so your egg white and your milk, sorry, form your insoluble precipitates with these heavy metals which can be removed by lavage. And so accordingly, in case of heavy metal poisoning with this mercury, silver, and lead, and so a good antidote is one of this. And so your egg white or your milk. And so because they form insoluble salts, and so they form insoluble salts, thereby they will not be dissolved and there is no absorption of these heavy metals that will take place. And so when there is no absorption that will take place, the effect of the metal is actually the effect of the metal is actually stopped, no, or probably reduced. Okay, and so you have there the egg white will make and your milk will form insoluble precipitates, and then of course they will hold, and so there is no distribution of the heavy metal, and so there is no absorption, then there will be no distribution, of course, and that the the insoluble salts can be removed by lavage or via stomach tube. And so you have here your agent. And so some actually of your results in the laboratory. And so you have your agent, and so you have at zero point 0.1 silver nitrate, copper sulfate, and 70% alcohol. And so with this, accordingly, since as what we talked earlier, and so this theoretically they should give a precipitate, no? And so all of this should give a precipitate when added with a mixed with a protein. And so precipitates that will follow, of course, color of the uh, the color of the reagent. And so you have your blue, and so somewhat blue and somewhat brown precipitates, and then white for your alcohol. Okay, and so that is for your uh, effect of your heavy metals. And then, okay, and so your effect of heat. And so accordingly, your solutions of protein when heated between 38 to 30 degrees Celsius undergo slight intramolecular rearrangement. And so giving a rise to a changes and the what they call this chemical, physical, and biological properties of and become denatured, no? And so you have there your 36 to 60 accordingly of your disruption of your bonds, unfolding of the structure. And so theoretically, and so at this temperature, and so there should be probably at such at probably at 60 there should be already a what you call this a reduction of your precipitates, no? And so, and at 85 to 90 then you have should have a mass of clump chains. And then, of course, at 35 to 40. So that is your initial. Okay, and so that ends your activity 18.